Atomic absorption spectroscopy, or ABS, is a technique for measuring the concentrations of metallic elements in different materials. As an analytical technique, it uses electromagnetic wavelengths, coming from a light source. Distinct elements will absorb these wavelengths differently. It gives a picture of what concentrations of a specific element there are in whatever material, or liquid is being tested. Here we look at what ABS involves as an analytical technique, what it can measure, why it is useful, and the instruments involved in carrying it out. Spectroscopy is the study of how radiated energy and materials interact. Matter absorbs energy, which will create some sort of the change in its state. The atomic part refers to the atoms in a material, which will absorb radiated energy from a light source. The atomic part refers to these atoms will each have their own characteristics when it comes to absorbing energy because each element has a unique electronic structure. Atoms in a material, which will absorb radiated energy from a light source. Therefore, using ABS, you can measure a specific element in a material, based on the amount of light absorbed at a defined wavelength, which corresponds to the known characteristics of the element you are testing for. As a phenomenon, atomic absorption spectrometry was first discovered in 1802, when the English scientist William Hyde Wollaston observed and described dark lines in the sun's spectrum. In 1817, the German physicist Joseph von Fraunhofer carefully mapped out these spectral absorption lines, which are now named after him. A theory of spectrochemical analysis was then developed with the work of the scientists Gustav Kirchhoff and Robert Bunsen in 1860. However, atomic absorption spectroscopy as a modern technique for chemical analysis dates from 1955, when the Lancashire-born scientist Alan Walsh published his significant paper on the potential for ABS in Melbourne, Australia. Atomic spectroscopy provides a high degree of accuracy. Normally results fall within a range of 0.5% to 5% accuracy, but this may improve further depending on the standards set for testing and analysis. It is a highly sensitive method of analysis. In a given material, it can measure parts per billion of a gram. In applications such as medicine and pharmaceuticals, ABS has helped revolutionize practices, detecting things such as trace toxins. In some sectors, this method has been able to detect elements that people were previously unaware existed in certain materials, such as cobalt and molybdenum in soil. Atomic absorption spectroscopy has different laboratory and testing applications in industrial, clinical, and research settings. As a crucial component in various processes, these processes include quality control, toxicology, environmental testing. Metals occur naturally in the world around us, and around 3/4 of the Earth's chemical elements are metals. Sometimes metal content in a material is desirable, but metals can also be contaminants. Elements exist on an electromagnetic spectrum, and their atoms will absorb wavelengths of light that relate to their particular characteristics. During the atomic absorption spectroscopy process, these atoms will absorb electromagnetic radiation at A. By looking at these signals, it is then possible to determine the parts per million, or ppm, levels of specified metals in the material that is being tested. What creates these signals? Within an atom, there are electrons at various energy levels. During the spectroscopy process, the absorption of energy moves electrons to a more energetic level. The radiant energy the electrons absorb is directly related to the transition that occurs during this process. Atoms absorb light in an excited state. The atoms absorb light in an excited state. Atomic absorption measures amount of light at a resonant wavelength, which passes through a cloud of atoms and is absorbed by them. A resonant wavelength absorbed by atoms emit energy in the form of photons and electrons. Every element has its own unique electronic structure. So the radiation absorbed represents a unique property of each individual element. The amount of a specified element present in a material is determined by measuring the amount of light absorbed and the energy emitted during the spectroscopy process. The changes in these wavelengths of light, before and after absorption, will appear as peaks of energy absorption in a readout. Metals tend to be good conductors of heat and electricity. Most metals have a high density but can be broken up into sheets. Most metals corrode if exposed to seawater or air. They can be shiny and ductile, which means you can make them into wire. Here is some of metallic elements that atomic absorption spectroscopy can measure: aluminium, antimony, barium, arsenic, beryllium, cadmium, calcium, chromium, cobalt, copper, zirconium, hafnium, indium, iron, lead, lithium, magnesium, manganese, mercury, molybdenum, nickel, zinc, osmium, potassium, ruthenium, silver, sodium,